Hey Ramblers, this video deals with chapter 1.4 in our textbook and deals with logarithms. Now logarithms are the inverse function, which we just talked about, of exponential functions, which we talked about 2 sections ago. So it's very topical that it comes up now. This video will deal with the most common types of logs that we deal with. The common log, which is the log base 10 of x, and the natural log, which is the log base e of x. So we'll explain and remind you a little bit of what logs are and how they translate to the more familiar exponential notation. Then we're going to take a brief review of the properties of the logarithms. We'll then jump into an example of how we need to use those properties to solve some of the algebraic problems when we have our variable up in the exponent. And then the last example we'll look at is a problem where it's dealing with an exponential decay problem and how logarithms help us to solve those very familiar problems that we had in the exponential form. Okay, Ramblers, thanks for watching. Please take good notes, pause often. If you have any more questions, you can get on Edmodo or bring them to class with you tomorrow. Thanks for watching. Let's start our discussion of logarithms, kind of looking at them in the context of how they relate to things we've just learned. And since we've just covered talking about inverses, let's think of a log as the inverse of an exponential, because it is the inverse of an exponential. You recall that exponentials kind of hug the x-axis and then they cross the y-axis and then they rise to infinity. The place they cross is at 0, often 0, 1, but 0 p naught if we want to borrow some of the terms we learned. Let's say that this equals y equals p naught times a to the t. So you'll recall that in our last video we talked about how inverses, their graphs are reflections over the line y equals x. Well, if that's the case, then a logarithm, which is the inverse of an exponential, is going to be the reflection over this line. So it's going to cross the x-axis at p naught, comma, 0, and instead of coming along and hugging the x-axis, it's going to come up, hug the y-axis, and then it's going to extend out to infinity that way. So this is the graph of a log. So let's take a look at a little better picture of it. All right, so let's put this up here and bring this other printed picture of the graph forward. All right, so let's take a look at some of the key elements of the graphs here. We see that the exponential, just as I said, grows to infinity. It crosses, typically, if we're looking at just a plain old exponential, it'll cross at 0, 1, because anything raised to the 0 power is equal to 1. And then if we compare it and reflect it over this line y equals x, we'll get the inverse of exponentials, and that's going to hug the x-axis as x grows to infinity. It will cross at the point 1, 0, which is the reflection of 0, 1. So logarithms have that look. Let's talk about the two most common, the common log, base 10, and the natural log, base e. All right, the common log of x, which is written just log x, we're very used to seeing just log x, is the power of 10 needed to get x. So we write it like this. If you're writing log base 10 of x, or you could just write that as log of x. It's the same thing. If there's nothing written, it's assumed to be base 10. When we write that, it means that 10 to c equals x. So in other words, this thing that a log equals is an exponent, and that may be the most important sentence you remember. The log is an exponent. Let's make sure that's in your notes. Now, how does that relate to log base e? Well, all right, when we talk about the natural log of x, we write it as ln x. Sometimes people call it line x, but stay away from that. Just try and call it the natural log. And the natural log is the power of e needed to get x. So, in other words, just like common logs, the natural log of x equals c means e to the c is x. Once again, a log is an exponent. So very important to remember that. Okay, let's move on to some of the properties of logs. Okay, we're not going to prove the properties of logs. You've been over that in pre-calculus, but I do want to remind you of them. They're really important. So let's quickly take a look. Okay. Let's remember that a logarithm is an exponent. So when we take a look at the column here on the left of log AB, since this expression log AB is an exponent, it's not surprising that when you're multiplying two things within the log, that it's represented as addition, because when you multiply, you add exponents. Likewise, with division, when you're dividing within the log, that is accomplished by subtraction, just as when you're dividing two numbers with a like base, you can subtract the exponents. Okay, number 3, when you're raising a log to a power, you can bring the power out in front. Very useful, as we'll see in the first example problem. And then be really careful with number 4, because it's an identity. It is saying that the log base 10 of 10 to the x equals x. That should make sense. The exponent that you need to raise 10 to make 10 to the x, well, of course, that's x. Number 5 is the reverse of that. If you're raising 10 to an exponent needed to make x, well then of course you're going to get x. All right, over on the right-hand column, it's the same properties, but they write it in or relative to e and the natural log. Make sure you're very, very comfortable with both sides of this chart, and certainly all 5 of the properties are important. Now, it's also important to recognize that the logs are not defined for negative numbers or when x is 0. And that should make sense. Once again, when you look at the graph of the logs, you'll recall that it hugged the y-axis and the x values were never negative or equal to 0. Finally, log of 1 equals 0 because 10 to the 0 equals 1. And likewise, the natural log of 1 is 0. Those are things you really should have memorized as calc students. So this is an important chart. Make sure you get it in your notes. Let's take a quick look at how we use logs to solve some problems in the next section. All right, we're going to put some of these properties of logs into action here. So suppose we were trying to solve for t in the equation 2 to the t equals 7. So we're given 2 to the t equals 7. The problem here is that our variable is up in the exponent, and we have to get it out of there. So the operation that we use to get something out of the exponent is we'll take the log of both sides. So I'm going to take the log of 2 to the t equals the log of 7. Now the hardest part to remember is that the log of 7 is a number. It's in my calculator. If you got an old math book, you could have looked it up in the back. So, but what happened over here on the left? Well, we're going to invoke that property number 3, and I'm going to bring that exponent out in front. So I have t times the log of 2 equals the log of 7. And just like log of 7 is a number, so is the log of 2. Not a pretty number, but it's a number nevertheless. So I can say that t equals the log of 7 divided by the log of 2. And when I do that and plug it into my calculator, I'm going to see that t equals about 2.81. That should make sense, because if I go back to my original problem, I know that 2 squared equals 4, and 2 cubed equals 8, and since I want 7, my answer should be a number somewhere between 2 and 3, and since 7 is closer to 8 than it is to 4, I'd expect my answer to be closer to 3 than it is to 2, which it is. All right, let's take a look at one more example, slightly more complicated because it deals with exponential growth, but also slightly more applicable. Suppose we know that the concentration of carbon monoxide in the air near a busy road was a function of the distance from the road, and that the concentration decayed exponentially at a continuous rate of 3.3%. We could then express the concentration using this expression. All right, how long would it take until the concentration of carbon monoxide was 1/2? Well, to figure that out, we would take 1/2 of C naught, or 1/2 of what we started with, equals C naught times E to the 0.033x, which is what represents 3.3% decay. Now, the C naughts are going to cancel out. So we're left with 1/2 equals e to the negative 0.033x. Okay, once again, that variable is up in the exponent. And as we learned in the last slide, the way to get the variables out of the exponent is to take the log of both sides. Since this problem deals with e, I'm going to take the natural log. So the natural log of 1/2 equals the natural log of e to the negative 0.033x. Now, we could use the property that the exponent comes in front, but let's stop a minute. This really deals with property number 5. What is the exponent of e needed to get e to the negative 0.033? Well, clearly, that's just going to equal negative 0.033 on the right side. The natural log of 1/2, well, that's just a number. I could look it up in my calculator, and if you do, it would tell you negative 0.6931. Now, to solve for x, I'm just going to divide both sides by the growth rate, and I'll get my final answer. And that is x equals about 21 meters. So you'd have to be about 21 meters away from this road to have to make the air have half the amount of carbon monoxide it did when you're right next to the road. Okay, Ramblers, a lot of things here. You have to really get down those properties. You really have to be comfortable with what the expression log of x and natural log of x means. And I certainly want you to be able to solve expressions that have an exponent in them using logs. Okay, we'll work through the exercises tomorrow in class. Thanks for listening and watching.